Recombination and photovoltaic performance. The management of recombination is essential for obtaining high-performance solar cells. We explained that in a solar cell, electrons and holes are created by light, and then they have to come to equilibrium, and they can do inside by recombination or make work in the outer load. There is a minimal amount of recombination. This is the radiative recombination that allowed us to study the radiative limit, which gives the maximal performance of the solar cell. And there can be additional bulk recombination processes in excess of the radiative recombination. And there can be also surface recombination at the contacts. These are different, and they all have to be identified and minimized. We discuss first the bulk recombination, and here we have, this is the one that cannot be removed. Then there is Shockley red hole recombination at intermediate levels, and there is non-reactive Auger, which is a collision when the density of carriers is high. Recombination is closely connected to the diode equation of the solar cell. In this simple initial model, we have a balance of internal and external fluxes, and there is the recombination current, which is depending on the voltage. Because the density of minority carriers is depending on the voltage, like the Boltzmann expression. But in general, we can use a recombination order, which is 1 over m. And this number m is the diode iterative factor. Because then the recombination current, which is proportional to the carrier density to this power, will be jota 0, and the exponential term with a generalization number m. And that goes into the final diode equation for recombination, and the m is describing how fast this power law at forward voltage is rising. So this term m comes into the current voltage curve of the solar cell on the illumination, and by finding the minimum, we already discussed that this number determines the fill factor at a given VOC. The ideal number for the Boltzmann statistics is n equals 1, which is this law, but at higher n, the fill factor is decreasing and the efficiency of the solar cell is decreasing. We recall the radiative limit of the photovoltaic. At one sum, this is a quantity smaller than the band gap because the Fermi levels are yet not touching the band gap. And this is the maximum VOC that can be achieved. And the radiative VOC depends on the incoming photon density logarithmically. Now, by including this diode quality factor in the JV curve, this law is going to change so that the dependence of VOC is linear with the logarithm of the photon intensity and with a number m and kBT over q. This is a way to derive the m. And here we can see an example of the radiative limit. In this case, m equals 1. But if we include the mechanism of Shockley red hole, then this is going to decrease the number m. It is about 1.5. And when going high, it will be dominated by Auger recombination, which with m equals 2/3. So in general, this VOC with respect to light intensity gives different slopes depending on the different mechanism of recombination in the bulk or also at the surface that are occurring in the solar cell. So here is an early example of the determination in a perovskite solar cell. So we can see that in the first case here, it's nearly 1 because this is for a pristine solar cell that has not been yet polarized. After going polarization and JV curve measurement, this diode quality factor was changing to 2, indicating a strong modification because of the ionic effects, etc. So that the measurement itself was modifying the perovskite solar cell, although this can later be recovered. And the same result can be obtained electrically by measuring the recombination resistance. We can obtain only the slopes associated to the recombination law, which is the number m again, and it changes if it is a pristine solar cell or already polarized and treated perovskite solar cell. In addition to the possible bulk recombination effects, we have to add the surface recombination effect. This is an additional loss occurring because of specific defect states at the surface, and this can produce very large loss of the photovoltaic. So in general, the effective lifetime of recombination of carriers will be the sum of the inverse of they are parallel processes. So we have the bulk lifetime and the effective lifetime at the surface, and this is related to the surface recombination velocity. The larger the surface recombination velocity, the shorter will be the lifetime at the surface. And this is a simulation of how the effective lifetime is decreasing by the impact of the surface recombination velocity that also depends on thickness because the carriers have a component of diffusion to the surface. And there is certainly a decrease of efficiency of the solar cell, and when the surface is improved and decreases the surface recombination velocity, it will increase the power energy conversion. And this graph summarizes the situation. We said that here we have for a solar cell, for example, the perovskite, here we have the band gap, and at one sun we have the radiative VOC, and this will be further decreased if there is bulk or surface recombination, affecting the JV curve. So this is mainly seen in the photovoltaic, but it will affect also the fill factor, as we said before. And then from the gap energy, we go to the radiative recombination, including solid red hole decreases further, and for interface recombination is further decreased. And in each case, we can see that the power energy conversion is the area of the square.